Welcome to this first colloquium of 2020. I will just tell you briefly about the next events. The second event will be on March the 4th, and it will be devoted to experimental particle physics. Then there will be another event devoted to quantum computing, April the 8th, and the following event will be devoted to algebraic geometry. It will take place in May, but we have not decided the date yet, unless you know it, okay. Then there will be one last event in June devoted to condensed matter physics, but we'll tell you more in due time. Thank you for coming.
So good afternoon. It's my pleasure and it's also an honor to introduce a colleague and friend of mine, Professor Gianfranco Bertone. Gianfranco is here in Pisa, I guess, formally for the first time to give a lecture at Scuola Normale. He has been here also for some outreach activities that we performed before. So Gianfranco studied in Rome, della Scienze, and then he continued for a PhD, joint PhD between Oxford and IAP, l'Institut d'Astrophysique de Paris in France. And then he got a number of positions as a lecturer, both in Padova, and IAP again, and in Zurich. And then he finally stopped or continue in Amsterdam at the University of Amsterdam. Where is he now? He is also one of the co-founders of the Grappa Center, which is not a place where you go and do wine tasting, but it's Gravitational and Astroparticle Physics Center in Amsterdam. That it's we consider it as a twin center of our newly funded graphic center that has essentially the same spirit here in Scuola Normale to study gravity and anything that has to do with large-scale structure and gravitational physics, including gravitational waves and black holes. And so Gianfranco has an incredible number of publications, very important publications, essentially in dark matter, not only dark matter, but certainly dark matter is it's his major expertise. He's been very successful in coordinating the work of many people. He's really a leading scientist in the field, and so he's an expert in theory of dark matter, but he's a fine also appreciation of all the experimental work that's been done. He's working in close contact with experimentalists. Last thing I want to say is that in addition to all this, he's also very active in all in outreach sector. He's doing public lectures, and he's also running a prize for popular books, scientific popular books. It's called the Premio Cosmos. It's based in Reggio Calabria, which is the place where he's coming from. And so it's a pleasure to have him here and learn about the latest news in dark matter.
Thanks a lot to everyone for being here. Thanks a lot to Augusto and Andrea for the invitation and for the very nice introduction. What I would like to do today is to tell you a little bit about a new era in the quest for dark matter. In order to do that, I will introduce first the dark matter problem. I will tell you why it's a problem and what has been done so far to understand this problem, and why I think that a new era has started in the search for dark matter. Now, I understand the audience is very broad, so I will not give too many technical details. I actually will not give technical details at all in this presentation. We'll try to convey the main message, behind the talk. But I encourage especially the students who want to know more, to come and see me after the presentation, and I'll be happy to follow up with more in-depth discussion and more technical details. Now, let me start with a very brief historical parenthesis. Because I think that the history of dark matter is a bit underappreciated, and we've been working a lot, together with a professor in the history of physics at the University of Amsterdam, to tell a more realistic, a more real actually story about how the scientific community came to accept the existence of an unknown form of matter in the universe. And typically, if you've been at a conference on dark matter, you probably have heard that Zwicky, this Swiss astronomer based at Caltech, has observed the velocity dispersion of galaxies in a galaxy cluster, and he coined the term dark matter. And then in the 70s, Vera Rubin discovered flat rotation curves, and then we had the dark matter paradigm established in science. Both statements are actually quite misleading, and this doesn't diminish the importance of these two giants of physics and astronomy. They played a very important role in establishing the dark matter paradigm. But the more you learn about the history of dark matter, the more you come to appreciate that a lot has happened also around this figure, and also before and also after the work of these giants of physics and astronomy. And I don't have time really to discuss all of this in today's presentation, but let me just mention that already in 1904, so we're talking about 116 years ago, this is before we knew that other galaxies existed in the universe. The known universe in 1904 is the stars of the Milky Way. Okay, so this is before the historical discoveries of Hubble. And what Lord Kelvin did back then, he has his kinetic theory of gases, basically thermodynamics, and he applied this theory to the stars in the galaxy, in the universe, which back then was the stars in our own galaxy. And what he tried to do was basically, something quite simple, to associate the velocity dispersion of stars with the gravitational potential in the galaxy we live in. And from there, he actually was reasoning about, what contributed mass, so therefore gravitational potential, and he insisted that, many of our stars, and perhaps a great majority of them, might be dark bodies. Okay, so he was using the term dark, essentially in the modern sense, so something that contributes mass, but and therefore influences the dynamics of objects in the sky, but can't be seen with our telescopes. And then only 2 years later, Henri Poincaré was reflecting on the work of Lord Kelvin, and he described his work by saying that his work was very interesting, and he said that based on the data that were available then, the total number of stars is comparable to which the telescope gives, and therefore there is no dark matter, or at least not so much if there is a shining matter. So he was using the term, first in French, matière noire, then in English, dark matter, already back in 1906, to mean something which is quite close to the modern meaning of this word. So I don't have time today to go through the long and fascinating history of this problem, but I put here two references to some work that we did together with a colleague whose name is Dan Hooper, and we published in this Review of Modern Physics. It's a pretty kind of thick, long review of the history of dark matter, and then this work that we are doing together with, I mentioned this professor in the history of physics, his name is Jeroen van Dongen, if I managed to get there. Anyway, so this guy here, Jeroen van Dongen, professor in the history of science, and we have a brilliant PhD student, Jago de Zwart, working on this problem. And we published a while ago this paper on nature astronomy that is called How Dark Matter Came to Matter, which focuses on in the period of the 1970s, which is where the big paradigm of dark matter was essentially established. This is a very appropriate moment to discuss about dark matter, because Nobel Prize in Physics in 2019 was awarded to at least for one half to Jim Peebles, for another half to Michel Mayor and Didier Queloz. And for the part of Jim Peebles, if you read the motivation for the Nobel Prize, you will see that for the first time the term dark matter is mentioned in the motivation. And in particular, the role of Jim Peebles is acknowledged in establishing this fundamental result that showed that showed us a universe in which only 5% of its content is known in the form of stars and stuff we know, planets, trees, and us. And the rest, 95%, is unknown dark matter and dark energy. And this is a mystery and a challenge to modern physics. Many of you have heard this statement, that 95% of the universe is dark. And I wanted to qualify a little more this statement, because I think it can be a bit misleading unless you know exactly what is that we're talking about. Now, when we discuss the evidence for this dark universe, we typically bring together in a sort of a self-consistent model, the standard cosmological model, as it is called, a wide array of observations that include rotation curves of galaxies, so stuff on the scale of really of the scale of our own galaxy, but also scales even smaller than that. Stuff on the scale of clusters of galaxies, and the analysis of these systems goes through X-ray emission, study of lensing, and so on and so forth. So we have different ways of estimating how much mass there is in galaxy clusters, and it systematically exceeds the mass that we can observe with our telescopes. And even if we didn't know anything at all about rotation curves of galaxies and clusters of galaxies, if we just get rid of all the evidence that we have from stuff we can measure with our telescopes, and only focus as an observable on the cosmic microwave background, or also called the CMB, that I show here. So this very kind of ancient light that is left after the Big Bang, that now we measure and study with great precision. Even by study only the CMB, you would have evidence in the universe of a component of matter that interacts with gravity, and only with gravity as far as we know. So it doesn't interact with normal matter, doesn't emit light, is invisible to our telescopes, and but it still influences the dynamics of the objects that we observe in the universe. And this is how this is typically summarized. This dark matter, which is 23% of the total energy and matter budget of the universe. There's 5% atoms, so everything we know about in the universe. And then it's commonly said that there's dark energy that dominates the matter and energy budget of the universe. And this dark energy is not some form of matter that kind of influences the dynamics of galaxies and clusters of galaxies. This is something that actually has the opposite effect. It has the effect of accelerating the expansion of the universe, making it expand ever faster. And discovery of dark matter dates back to like the 70s, essentially 1970s, 1980s. Discovery of the accelerated expansion of the energy, which is interpreted in forms of an additional form of dark energy in the universe, dates back to 1990. I said that this statement can be a bit misleading, and the specific, what I really mean with that is that this is a statement that is valid now, in this particular moment in the history of the universe, and only on a particular range of scales, of length scales in the universe. So it doesn't reflect something fundamental, or at least it is a statement about something fundamental, about what is going on in the universe, but what is fundamental is not the number, the 95%, which reflects a particular moment in the history of the universe, in particular length scales, but the fact that we have these different components that are evolving in the history of the universe. And to make this more clear, let me just mention that if you take a sphere in this room and just take the volume of this room and look what inside this room, and you ask what is the contribution of atoms, dark matter, and dark energy? Well, it's essentially 100% atoms. Right? The density of dark matter, the local density of dark matter, as it can be inferred from astronomical measurements, is of order 0.3 GeV per centimeter cube. Okay, so this is a very small number. So this is 24 orders of magnitude smaller than the density of water. Okay, now even if you consider air, it's still order 20 orders of magnitude less dense than the normal matter.
What kind of atom?
Yeah, molecules of air in this room. And the contribution of dark energy is even smaller. Now, if you take another range of lengths, if you take a sphere of 20 kiloparsec, or if you're more familiar with these units, 65,000 light years, you will see that dark matter contributes 72%. You start to pick up the contribution to the mass that comes from dark matter, which is largely in the outer parts of the galaxy, and 28% is in the form of atoms. And these things, they're not just guesses. You can measure these things quite precisely. And this is a reference to an article that did precisely this kind of exercise, of determining what is the contribution of stars and gas, which are bundled together in atoms here, and what is in the form of dark matter that you cannot see. Then, even if you consider the very large scale, so the statement I made, the 95%, is true only if you consider something which is on very, very large scales, on scales on which the universe is on average, homogeneous and isotropic. But even if you consider the universe as a whole, and you look back in time, the relative contribution of dark matter, dark energy, and atoms was very different in the past. So for instance, if you're interested in the question, how structures started to form in the universe, how did you form galaxies and, and stars and planets and so on, these structures started to form, for the experts in the room, at recombination, right? When the CMB was emitted, essentially, that's where you started to, you traditionally start the epoch of structure formation in the universe. If you look back then, so this is, the universe was around 400,000 years old when this, for what concerns this slide, the relative contribution of the different species was very different. Dark matter, 63%, atoms, 12%, but you still had what is called radiation. So relativistic particles like photons and neutrinos, they contributed a lot to the matter and energy budget of the universe. So you really need to be kind of very careful when you want to kind of really understand this concept of 95% of the universe is dark. And the best way to visualize this, let me skip this slide, the best way of visualizing this is to plot the density of different species as a function of the age of the universe. Okay? Because if you look at percentages, it's kind of very difficult to understand what is going on. You see the percentage of the known universe going basically from 100% in the early universe to 0% in the distant future of the universe, as if the universe was becoming more and more unknown as time goes by. But this doesn't really capture the physics of what is going on. This is maybe more easy to visualize. If you plot the density, the evolution of the density as a function of time for different species, so for instance, everything which is in the form of atoms and lights and neutrinos, everything which is in the standard model of particle physics, you see that it continuously declines as the age of the universe increases, and this is just a simple consequence of the expansion of the universe. If you have a fixed amount of matter in the universe, make the universe expands, then the universe just goes down in the epoch of matter domination, just as 1 over the radius cube, basically the volume of the universe. However, what remains constant throughout the age of the universe is the density of this mysterious component of the universe that we have to invoke to explain the data, which is dark energy. Okay, it is as if there was a sort of energy density which was connected not to the amount of matter that we have in the universe, but with the vacuum, essentially, with the space-time itself. And we're still, I think we're kind of very far from understanding what the true nature of dark energy. We might be closer to understand the nature of dark matter. And the main point I wanted to make is really that if you want to understand our the origins of the structure of the universe, dark energy really didn't play a major role in that sense. Okay, so all of this might sound crazy to you if you're not familiar with these concepts. But if nothing, if all the the data and the analysis of the data and so on and so forth that we put together didn't convince you, something that might convince you is numerical simulations of the formation of structures in the universe. What you see in this movie is it's a natural numerical simulation. It's just not a visualization of how structures form in the universe. This is a natural numerical simulation that starts from initial conditions that are imprinted on the cosmic microwave background, so things we can actually observe. Now, this is mainly dark matter that is forming structure, but if you look at structures like this one here, you will see that at some point, a couple of billion years after the Big Bang, something interesting starts to happen in those simulations. And what is happening there is that, dark matter is kind of, at least as far as we know, the dynamics of dark matter is kind of boring. It doesn't interact much with itself. But we know that normal atoms, they do much more than that. They form stars, stars explode, they inject gas in the interstellar medium, and so on and so forth. And these simulations actually capture a lot of the physics that is happening in the formation and evolution of the universe. And the universe you get at the end of these numerical simulations actually looks a lot like the universe we observe. And it's not just another qualitative statement. This is really a quantitative statement about the type of galaxies you form and all the statistical properties of the universe you form. So it seems that the standard cosmological model is really capturing something fundamental about the physics of the universe. The question is, what are these mysterious components of the universe? What is dark matter? What is dark energy? Because until we find an answer to these questions, we have something which is more like a conjecture rather than a trusted model of how the universe works. And that's the topic of this conference. What is in particular dark matter? We'll focus in particular on dark matter today. And the first question I want to ask is, what do we know about these particles? So let's assume that it is true that there is this mysterious component of matter and that is showing up in all this data that we have. Let's assume that this is actual. This is an actual form of matter out there. What do we know about these, the fundamental constituents that are behind this dark matter? And in this slide, what I do is I kind of arrange the information we have on the nature of dark matter based on the number of observations we can perform about its properties. And in particular, I ask here, what are the properties that a new particle needs to fulfill in order to be considered a viable dark matter candidate? Now, the first condition is that the abundance of this new particle in the universe has to satisfy current constraints. And we know the abundance of dark matter in the universe with very good precision, of order 1%, mainly from cosmic microwave background measurements. So not only we need to not only to propose a new particle, but we also need to propose a mechanism to produce these particles with the right abundance in the early universe. We know that these particles must be cold, and this word cold can be made very specific. It must be non-relativistic, essentially, so moving slowly when structures started to form, a typical structure formation. Okay, and this sets pretty stringent constraints on physical quantities like the free streaming length, the mass of the particle, and so on. It must be neutral. There should be no couplings, so there should be no charge, no electric charge, no color, nothing that gives these particles too large interactions with the standard model of particle physics. It must be consistent with everything we know about things like Big Bang nucleosynthesis, so the formation of light nuclei in the early universe, which is pretty constraining, and also what we know about stars. We have a theory of for this formation and evolution of stars that works very well. You'll be surprised to see, if you haven't worked in this field, you will be surprised how difficult it is to produce a particle, is to propose the existence of a particle that doesn't mess up something in the universe. So for instance, if your particle is too light, it could take energy away from the center of stars, and you can have stars collapse and produce black holes and all sort of crazy things that can be readily ruled out just by the fact that stars exist in the universe. And you can do a lot of precision physics. There's people connecting this, for instance, with heliosismology, so the study of the vibration modes of the sun, for example, and the properties of how the speed of sound varies in the interior of the sun and things like that. Now, there are 10 points in total. I really don't have time to go through all of them in this presentation, but let me just mention that there are a number of experiments that constrain the interactions of dark matter particles with themselves, so they can be assumed to be rather collisionless to very good accuracy. We know that the couplings of dark matter with the standard model must be very small, otherwise we would have seen these particles in direct detection experiments, and also with other astrophysical observations. And we know that the self-annihilation of these dark matter particles, or the decay time of these particles, should satisfy pretty stringent constraints that come from astrophysical observations, like observations of gamma rays, synchrotron emission from the center of the galaxy, high energy neutrino emission, and so on. I will not discuss much all of these particular constraints, but if you're interested, feel free to ask me questions after this presentation. I'll be happy to discuss that. In this 10-point test that we had put together a few years ago, we also added a 10th point, which is that if you want to propose a dark matter candidate, there should be, at least in principle, a way of testing of probing your particular model. So it should be possible, at least in principle, with a technology even kind of 100 years from now, to measure these particles in laboratory experiments, right? Otherwise, it can hardly be considered. Maybe that's what nature has chosen, to find a particle that doesn't interact with anything. But in order for it to be science, we need to have at least conceptually a way of probing the nature of these particles. What are we left after all of this? Well, you can readily rule out all the particles of the standard model. If you go systematically through all the known particles of the standard model, none of them have the right properties to satisfy all the properties for the requirements for dark matter. For some time it was thought that standard model neutrinos could explain the dark matter, but they don't satisfy a number of the constraints we just discussed. In particular, they're not cold, they're not non-relativistic at the epoch of structure formation. Their free stream length is too long. It's very difficult. It's impossible essentially to explain the structures as we know them in the universe with neutrinos. What are we left? Well, physicists are very creative individuals, and there are many models out there. And in this review article that we published now a year and a half ago, what we've tried to do was basically to organize the ideas around what dark matter could be, around the main question of what dark matter could be in this kind of mind map. And what you see here is, we'll not go through it because it will be a bit boring and also, outside the scope of this particular presentation. But let me just go through these, big blobs here. Let me just mention that, light bosons like QCD axions and other ultralight particles have long been considered as, compelling dark matter candidates. Another possibility is that dark matter has something to do with the neutrino sector. I mentioned that standard model neutrinos cannot be all of the dark matter, but certainly contribute some of the dark matter in the universe. And there are a pretty large community interested on the possibility that by extending the neutrino sector to the possibility that there are some sterile neutrinos, so there are cousins of the standard model neutrinos, you could explain dark matter. Another possibility is that dark matter has something to do with the weak scale in particle physics. And the weak scale, it's a particular scale in physics at which, many scientists thought, for completely different reasons, that there could be some new physics beyond the standard model. So there's a connection that, started to happen around, the end of the 70s, early 80s. And an enormous effort has gone in the exploration of these candidates at the weak scale, in particular for what concerns extensions of the standard model like supersymmetry. Then there is the possibility that dark matter has, in some form of other particle, and there are really many suggestions and many ideas that have been proposed in this field. There is the possibility that dark matter is some macroscopic object. If it is a macroscopic object, it's certainly not in the form of dwarf stars or stars that are too dim to be observed. There really needs to be compact objects that are not made of baryons, that are not made of atoms, essentially, because we get such very strong constraints from Big Bang nucleosynthesis. And there is still the possibility that we haven't understood gravity. We don't understand gravity on the large scales in the universe. Right? So the evidence for dark matter comes from imposing or from assuming that the range of validity of general relativity extends to all scales in the universe. Okay, so there's a community of scientists who think that maybe by playing with the laws of gravity, with general relativity in particular, you can get rid of the dark matter and the dark energy problem. Unfortunately, these theories fail to address some of the main the strongest evidence that we have for dark matter. In particular, it's very difficult to explain observations like the cosmic microwave background, the spectrum perturbations that we observe imprinted in the cosmic microwave background, and I will not further discuss them in this presentation. If you're interested, I'm happy to tell you more at the end. Now, what is dark matter? We've arranged it in the form of a mind map, but I think a spectacular way of seeing how uncertain this field of research is in terms of not in terms of really make predictions for what concerns the evolution of the universe, the formation of galaxies and so on, but really in terms of understanding the fundamental nature of dark matter. What you see here are different candidates, some of the leading candidates arranged in terms of the dark matter mass, the dark matter particle mass. And what you see is that the candidates range from 10 to the minus 20 electron volts to essentially 10 to the 70 electron volts, 10 or 100 solar masses. And I don't think you've seen many times in any field of science an uncertainty of over kind of 90 orders of magnitude in the mass of in a physical quantity of something that you're studying. The other thing is that most of these candidates have been proposed quite some time ago. Most of them in the 70s and in the 80s. So the height, I forgot to mention what is the height of the different columns. So the width of these different columns denotes the range of masses that describe these various candidates. You see that the highest column here, so the height of the column is roughly proportional to the number of papers that have been published on a particular candidate. And as you see, there's a clear winner in this competition, which is WIMPs, weakly interacting massive particles. And a lot of effort has gone into the search for these particles. Now, what is the main idea behind the WIMPs? The idea is basically that the idea is quite simple. I see I need to speed up a bit. The idea is quite simple, but very powerful. The first, so if you give a theoretical physicist the possibility to identify a mechanism for the production of these particles, one of the first ideas you could have is basically to put a particle in equilibrium, in kind of thermal and kinetic and chemical equilibrium with everything else in the universe, with all the baryons that you have, all the particles of the Standard Model. And what you do is basically to follow the equilibrium that you get by annihilating dark matter particles into particles of the Standard Model and vice versa. Okay, this is how you couple your dark matter with the Standard Model sector. Now, if you write down the equation that regulates the evolution of the density of these particles as the universe expands, you have an equation that probably resembles an equation that in whatever field you work, you probably have something like this. You have a term that describes the equilibrium between the two species. So there are these particles that annihilate into particles of the Standard Model, and these terms tell you that they are trying to that the number density of these particles tends to an equilibrium density. And this, the difference in this case is that you have another term, this H, this second term on the left-hand side that contains an H, and this H is actually the expansion of the universe, the Hubble rate that describes how the universe is expanding. So it's an evolution of the number density in an expanding universe. And what was realized long ago was basically that if you have an annihilation cross-section, this sigma v, which is at the scale, has at the weak scale in particle physics, then you produce these particles exactly with the right relic abundance. It matches the relic abundance you get from measurements of the cosmic microwave background. And this was incredibly exciting towards the end of the 70s, early 80s, because people realized we have for completely different reasons, people had postulated the existence of new particles at the weak scale. And these particles, through this mechanism, by being kept in thermal equilibrium and chemical and kinetic equilibrium with everything else in the universe, could explain the dark matter in the universe. So in the past, since the early 80s, a lot of effort went into the search for these weakly interacting massive particles, with accelerators, so the accelerators, you try to produce directly these particles through the collision of high energetic particles. With direct detection experiments, where you build an experiment, you place it deep underground, and you wait for dark matter particles to interact with your detector. And with indirect detection, so the search not for dark matter particles themselves, but for the products of the annihilation or decay of these dark matter particles as they interact with each other. Now, despite an enormous effort that went into the search for these particles, no WIMPs, nor any other dark matter candidate, as a matter of fact, has been found, at least not in a convincing way. There are a couple of hints here and there, and I'm happy to discuss them with you if you're interested. But I think it's fair to say that there is no convincing evidence of any WIMPs or any other particle in any of the experiments that have been run. And different experiments, I will not go through this, but different experiments, so for instance, searches for new particles at the LHC, or direct detection experiments and so on, they publish different versions of the so-called exclusion plots. That is basically the information that we get from these experiments. We haven't identified dark matter, but we have been able to rule out a lot of the candidates that have been proposed so far. So we excluded large regions of the parameter space. Okay, so then the question is, are WIMPs ruled out? And my answer to this question is big resounding no. And I'll give you like a one-line argument. And for the experts in the room, I have a dedicated slide, but maybe in view of time I will skip it. And I'm happy to discuss it if you have questions right after the presentation. The one-line argument is that absence of evidence is not the same as evidence of absence. Okay, so there's a lot of sociology that goes into there. You propose a candidate, you search for a candidate, you don't find it, then you say, okay, let's throw away the whole idea. But of course, there are many, it's a very kind of subtle and nuanced argument that you have to rule out an entire class of candidates. And I think it's completely straightforward for any theorist to come up with a WIMP candidate that survives all current tests. It's a fair and valid question. Can you even rule out in principle the existence of these WIMPs? But this is part of precisely what I want to address in the second part of my talk. And this is the more technical slide that I had for my colleagues who are experts. And if you're interested, just ask me after the presentation. I'm happy to go back to this slide. But I want to come to the key message that I had for today. Why, now that we have established the dark matter paradigm, now that we have said that, what is that we've done so far to search for these particles, and now that we know that all these searches haven't led to a clear identification of dark matter, the following question is, what do we do now? Shall we continue existing searches? Should we do something different? And if so, what? And I've organized actually these, last, let's say, 15 minutes of this presentation around three main points that I wanted to make. And, those of you who are interested in the details, here I've put a reference. This is an article we wrote with my colleague Tim Tate about a year ago. And, here you can find more, technical details about all of this. But the 3 points I wanted to make is the following. In view of the current status of dark matter searches, I think it is important to improve and also diversify the type of searches that we are performing. And point 2, to exploit astronomical and cosmological observations, which are achieving or are about to achieve the precision that we need in order to attack this problem. And third, there's a whole field of research that we just started recently, which is the field of the observation of the universe with gravitational waves. And what I want to do is basically to give you one example for each of these three. These are really, three fields of research, so I cannot possibly make justice to these three fields of research in a few minutes, but I want to give you at least one concrete example in each of these three fields to help you visualize what is happening in the community and what I think is the best way forward. Now, the first point I wanted to make is, we've been searching for dark matter at the LHC, and we've been performing searches based on our understanding of possible extensions of the standard model of particle physics. This animation shows what happens inside the LHC. So you have bunches of protons that are injected in opposite directions through pre-accelerators, then through the big accelerator. People write Lagrangians on the walls of the Large Hadron Collider. And then, this animation goes into the beam pipe, essentially. You see, a proton with the quarks inside the proton. And these particles are, accelerated at very, very high energy, and they're made to collide at the center of, big detectors, like the Atlas detector that is depicted here. And then what you do is you collect all the particles that are produced in these collisions, and you analyze them, and you search for these new particles with suitable techniques in the data. You can imagine how difficult it is to solve this problem, but scientists have devised extraordinary techniques, especially to sort out everything that happens in these collisions and to manage this enormous flow of data with exquisite precision. Now, one thing that is happening is that people are getting more and more interested in machine learning tools to explore this enormous amount of data, and these machine learning tools are enabling different ways of searching for new physics in the collisions that you realize at the Large Hadron Collider. Now, the bottleneck from many of these searches, if you have these multi-dimensional parameter spaces of new theory, was basically that if you want to go from your model, so for a particle physicist to write a model is to write a Lagrangian, essentially. So a Lagrangian that describes the particle content and interactions of your theory. But then if you want to compare, if you want to understand what the data tell you about your theory, you have to go through an intermediate stage, which is that first you need to calculate for that particular Lagrangian what is the so-called phenomenology, so the type of events that can, and collisions and topology of events and number of jets and number of leptons and things like that can happen in these collisions. And then you have to feed this phenomenology into a simulator. So this simulator will tell you exactly how the phenomenology that you're simulating can be directly compared in terms of number of events and things you can measure in your detector. Now, this step is very expensive, to go from the model to the data, and typically requires supercomputers to run this process. What is happening now is that it is possible to build surrogate functions, basically, that allow you to go from model to data without running these very expensive simulations. You still have to run them in order to generate your training set. But once you've done that, you can do directly the comparison at a fraction of the computational cost that you had to spend by doing the full exercise. And many people have taken the challenge, taken up the challenge of addressing this general problem of searching for new physics. One thing I wanted to mention is that there's this new collective that is called Dark Machines, which is really dedicated to the application of machine learning to particle physics and cosmology, with particular interest on particular attention, particular focus on dark matter. And if you're interested, we have the third workshop of this collective at CERN at the end of April, 27th of April, 1st of May. So you're more than welcome to join us there if you're interested. Now, let me go quickly to the second and third example I wanted to make about other things that we can do to search for dark matter in the future. I mentioned that astronomy and cosmology are getting to a point where the precision of the data allows you to do well, not precision physics in the sense of particle physics, but certainly, way more precise than it was possible, 10 or 20 years ago. And I think, time is ripe to, make use of this information to exploit astronomical surveys and cosmological data to search for dark matter. And to give you a visual example of, what you can actually do, let me show you another numerical simulation. This time it's not the formation of structures on very large scales, but this is a numerical simulation of a galaxy like our own. Okay, a galaxy like the Milky Way. And what you see here is basically this is a dark matter only simulation. There are no stars and there is no gas. And the reason why I'm showing you this particular simulation is to show you that if you want to assemble the dark matter halo of the Milky Way as we measure it with our data, this has to go through the merger of many small scale clumps, basically, that merge together and form larger and larger halos at the center of these large configurations. So it's a sort of a bottom-up process that puts together, by merging many of these small halos, builds a larger halo of dark matter. Okay, and this is, for once we have a very clear prediction that comes from this theory of so-called cold dark matter. The prediction that this paradigm makes, which is the standard paradigm for cosmology, is that there should be many of these small clumps of dark matter distributed in a galaxy like the Milky Way. Okay, so if you could probe these small scale clumps, you would probe a key prediction of dark matter, and you could even say something about the particle nature of dark matter, because depending on the properties of dark matter, you would get different type of substructures. How do we use this information? Well, now we have extraordinary data that are coming from satellites, astronomical satellites, such as the Gaia satellite of the European Space Agency. And what the Gaia satellite is doing is basically a big full sky view of the Milky Way. And this is not a photograph of the Milky Way. It's not like a snapshot as you would see in other data. You can imagine this as a sort of a scatter plot. They measure individual stars, a billion stars in the Milky Way, and they can reconstruct their distribution in the sky and their dynamics in the sky. Now, why is this interesting for us? Well, one thing that the Gaia is helping us enormously to do is to reconstruct so-called stellar streams. Stellar streams are the consequence of the tidal disruption, as we say. So if you take, suppose you have your galaxy, your disk of stars and gas, you throw a globular cluster, well, a cluster of stars in this, in the gravitational potential of the Milky Way. Because of tidal interactions, this globular cluster will be stripped and elongated in a sort of a one-dimensional stream of stars that wraps around the Milky Way. And this is not a conjecture. We observe tens of these stellar streams, stars moving in a coherent way across the sky. Why is this interesting for us? Because you have a very sensitive probe of the gravitational potential of the Milky Way. If it's true, as dark matter, the theory of cold dark matter posits, that you have a lot of these substructures in the gravitational potential of the Milky Way, then these substructures would interact with the stars of the stream, and instead of kind of a smooth density of stars along the stream, you could have gaps and perturbations all around, induced by the gravitational interaction of these subhalos with stellar streams. Do we see these interactions? Well, this is very recent work that is people in my group and in several other groups in the world we are doing to figure out what exactly these data are telling us. But let me show you this recent paper of a few weeks ago. What you see here is a plot of the stars if you look at the top panel, the stars in the stream as a function of phi1, which is an angle along the stream, and check out the extension of the stream. We are talking about stuff that occupies almost the entire sky, essentially. And phi 2 is the angle orthogonal, basically, to the angle along the stream. And what you see is basically that we have a lot of information about how stars are distributed, what is their velocity, and so on. If you look statistically at how stars are distributed, I don't have time to describe these plots in detail. I will go back if you're interested. This is a statistical analysis of the perturbations that you see along the stream, how much the linear density of stars in the stream is perturbed with respect to the uniform case, which would be the absence of subhalos. And what you're starting to see is that in order to explain the gaps and the inhomogeneities in the distribution of stars, you need to invoke the presence of subhalos in the Milky Way, of dark subhalos in the Milky Way. And this is not a fit. This is just, if you just take the amount of subhalos you get from numerical simulations, and you just put it on the same plot with the data, basically the prediction, which is the blue shaded region in this plot, goes through the data points. This is very preliminary. This is the first attempt we make to this type of analysis, but it seems to me it's very promising. And already several groups have taken up the challenge of constraining the particle nature of dark matter with this type of observations. In the last 5 minutes, do I have 5 minutes? Okay, in the last 5 minutes, I want to tell you about this third point, and then I'll wrap up. And if you have any questions, I'll be happy to discuss with you. The third point is that we want to exploit also the potential that arises from gravitational waves. I mean, of course, here in Pisa, very well the fact that you're perfectly aware of the fact that gravitational waves have been discovered. The Nobel Prize has been in 2017 has been assigned for this discovery. That the first discovery was about a binary with primary black hole mass. Were 36 solar masses, secondary black hole, 29 solar masses, and now people have produced these plots where you have all the information that arises from the LIGO and Virgo collaboration. You can start to build a census of black holes in the galaxy, at least black holes in binary systems. Why is this interesting for dark matter? Well, there are many reasons to expect that as black holes form, as astrophysical black holes form, but also primordial black holes, for those of you who are interested in those objects, you would form overdensities of dark matter. Okay, if this is true, and I'm happy to try and convince you that this is actually the case, you can study systems like this. You can have black holes dressed black holes. So in principle, black holes are very simple objects, and because of the no-hair theorem, you shouldn't be able to discriminate a black hole from another. But in reality, black holes, they carry a signature of their formation process. And this is imprinted in their mass function and also in the surrounding, so the environment around these objects. If they form in dense dark matter environments, they would carry this dark matter dress. And look what happens when you merge objects, black holes, they carry a dark matter dress. So typically, if they were moving on, they're still quite far apart. In principle, you would expect them to move on sort of elliptical Keplerian orbits. But you see that the presence of dark matter through dynamical friction is inducing a sort of a dissipation in the system. So the energy that was originally in the binary is transferred to the distribution of dark matter. So if you look again at this simulation, you start to see that dark matter. If I can go back, let me try again. Dark matter at the beginning is clustered around these black holes. As the system evolves, you will see that dark matter particles become unbound, right? And that the binary shrinks, so the separation between these two black holes shrinks, and you also change the eccentricity of the system, which also has important implications for the gravitational wave emission. Now, the net effect that we're looking for is basically a dephasing in the waveform. Okay, so if you change the evolution of the binary, you change the number of cycles, essentially, or the phase of the system. And in principle, with future interferometers, you should be able to follow the merger over many of these cycles, and you can search for these environmental effects produced by dark matter, induced by, around merging black holes. So it's just one example. I had another example on primordial black holes, but I think my time is up. Let me just mention that if you have an interest in this particular connection between gravitational waves and dark matter, we put together a white paper a few months ago, and I'll leave the reference to this article here. And let me conclude. I think it's fair to say that this is a time of profound transformation in the field of dark matter, in view of the absence of evidence for popular candidates. And I've stressed that this doesn't mean that existing candidates, what candidates people have discussed so far, are not there. But the way we don't have anymore a very compelling case for a particular class of candidates. The field is again completely open. The LHC indirect detection and direct detection experiments will still, may still reserve surprises. But at the same time, I think it is urgent to diversify dark matter searches, to exploit astronomical observations, and to exploit gravitational waves. And the last point, and this is especially for the young people in the audience, when you hear about crisis in science or in physics or in cosmology, you shouldn't take this as sort of a negative statement about the status of a particular field. We're not doing finance. People are not losing money because of that. Actually, on the contrary, this is an exciting and extraordinary opportunity, I think, for new generations to come up with new ideas and discoveries. Thank you.
So if there are questions or comments.
From the examples that you discussed at the very end, I get that, of course, you said that the important thing is that there will be new measurements that are important and has to be followed. I understand that you do not give weight to people that claim that there are already problems at relatively short distances and.
Well, my statement or my comment on that would simply be that, my impression is that those problems arise in the regime where we understand less the effect of baryons, so of standard matter. And in particular, I think you're referring to the so-called, small-scale problems of dark matter. The fact that numerical simulations, given the status of numerical simulations, where a lot of the physics that happens on small scales is implemented at the subgrid level, as they say, so in a sort of an effective way, without really describing the physical processes that happen on those scales. The fact that there is no perfect match between those predictions and the observations do not bother me too much, honestly. I think it's important, to follow them and to perform, better and better numerical simulations and better observations. But, I've been in the field now for, 15 or 20 years, and I've seen a lot of these problems, come and go, essentially when the right physics was implemented. So I'm not particularly concerned. I don't want to dismiss them because I know that people, feel strongly. Some people feel strongly about that. So I want to dismiss them completely. But I don't feel that they are, such a big challenge currently to our understanding of dark matter.
More questions?
Thank you for the very nice presentation. Can you show again this very nice scatter plot of Gaia? There was
Sure.
Just a technical curiosity. There was a white spot there, and I wonder what it is. Yes. Yes.
The white spots on the
yes.
bottom? I think those are the Magellanic Clouds.
Okay. Thank you.
If there are astronomers in the room, they might correct me, but I think that's what it is.
Sorry. My question will be naive. You and I are walking through dark matter in this room. It's okay?
Yeah.
Then you said that it's made of atoms.
No. No, I didn't say it's made of. I know that it's not made of atoms.
It's not made of atoms.
It's not.
Whatever that means, to be or not to be.
As I say.
No, no. Or what would it be made of?
That's exactly the question we're after. If you want an analogy, it should be something very similar to neutrinos of the Standard Model. We know that neutrinos exist in the Standard Model. We know they interact very weakly with the particles of the Standard Model. We know that through us, there are many, many neutrinos. And what happened in the case of neutrinos, we were able to build, big detectors that can catch these neutrinos. So you can actually now, you can photograph the sun when it's, below, on the other side of the Earth, basically, just by taking a snapshot of the neutrinos that are going from the sun through the Earth and then through the detector. Okay, so we hope that at some point for dark matter, we will be able to do something like that. So we're building, bigger and bigger detectors to try and catch those particles. But, the big difference with respect to the neutrinos is that in the case of neutrinos, we really had a very clear theory, very clear predictions about, what we should, the type of experiments we needed to build to catch these particles. We had a guess for many years about what dark matter could be, and the experiments we built to catch that type of dark matter so far failed. They will continue for, certainly for the next 5 or 10 years. But for the moment, we weren't able to trap dark matter as we do with neutrinos.
So I also have a simple question. So can you rule out that it's composite, the dark matter? Does it have to be an elementary particle?
No. For what we know, it could be. So for each, we cannot rule out the fact that it's composite. But whatever specific candidate you have in mind, it has to go through all the constraints that we discussed. So in particular, you don't want your composite dark matter to be in conflict with Big Bang nucleosynthesis constraints or with CMB constraints and so on. But dark matter could be atoms of dark matter. People like to make this analogy. Say imagine that you are in living in the dark side of the universe, and you're wondering what lives in the 5%, right? And then you say, well, it's one particle, right? And of course, we know that the structure of our Standard Model, what we call the Standard Model, is way more complicated than one particle. On the other hand, there's a large, sizable fraction of the community that explores the possibility that the dark sector, as they call it, is more complex than a single particle. So you have atomic dark matter and so on and so forth. Most of these theories are based on sort of Occam razors type of arguments, where let's start from something simple, or let's just assume that in this dark sector there will be one major particle that is playing the role of leading, contributing the largest providing the largest contribution to the mass of this dark sector, and let's search for that particle. But in principle, you can conjecture anything as long as that it satisfies those constraints.
But it's still such that the dark matter was created at the Big Bang?
So we know for sure. So we have constraints that come from Big Bang nucleosynthesis. So constraints that come from a few minutes after the Big Bang. And we have very stringent constraints that come from around 400,000 years after the Big Bang, which is the cosmic microwave background. So whatever you do, you need to satisfy those constraints, and those are pretty stringent. When I was saying that, it's very difficult to propose a dark matter candidate that doesn't mess up something. Some of these gets in conflict with some of these experiments. I really meant that it's if you whatever theory you have to make sure that it doesn't conflict with all those experiments.
Yes, I would like to understand what are the sufficient arguments, on the basis of what we have seen so far, against the proposal.
against the hypothesis of primordial black holes being one important component of dark matter? So,
well, as you probably know, when LIGO detected these very massive objects in the first detection of direct detection of gravitational waves, a large part of the community got interested in the question, can the objects that we see in LIGO explain the dark matter in the universe? And the reason for that is that I'm not sure I have, let me see if I have a plot here that I can show you. Not here, but I'm happy to show you to show this plot to you later. But basically, you can plot on the y-axis the fraction of the dark matter in the form of primordial black holes. So when it's 1, all of the dark matter is in the form of primordial black holes as a function of the mass of the primordial black holes. And everything below 10 to the minus 16 solar masses, something like that, is ruled out because of constraints on evaporation of these objects. Everything above 10 to the 3 solar masses is ruled out on the basis of some arguments about, it would perturb, to put it simply, the cosmic microwave background. These objects would accrete in the history of the universe and they would distort the cosmic microwave background, and we don't see those distortions. So there's this range between 10 to the minus 16 and 10 to the 3 solar masses, but in principle, these objects could explain all of the dark matter. Now, in the past 20, 30 years, people have started putting more and more constraints on this possibility. For objects around 1 solar mass, the most stringent constraints come from lensing, micro-lensing. We would see micro-lensing events from around galaxy. At smaller masses, there are constraints that come from femtolensing, from the analysis of white dwarfs, and various other astrophysical constraints. And even around tens or hundreds of solar masses, we started to see that it's very, very difficult to reconcile. To make f equal 1, so all of the dark matter in the form of primordial black holes consistent with observations. There is currently a very small window on very small masses where this is still possible, but we're talking there not about solar mass objects. We're talking about 10 to the minus 15, if I remember correctly, solar masses objects. So objects the mass of an asteroid, let's say, with, of course, a tiny, kind of microscopic scale, of course, because the size of those, the Schwarzschild radius of those objects is really, 10 to the minus 15 times 1 kilometer, right? So 10 to the minus 12 meters. So that's still a possibility, and there are many people trying to figure out, A, whether you have a compelling mechanism to form these objects in the early universe with the right abundance, and 2, to try and see whether you have ways of probing those objects and either rule them out or to make a case for them.
There was another question here.
Sorry. Thank you.
Sure.
I parked the car and I will get a visible ticket.
All right.
I'm sorry.
No worries. Yep.
If we assume that some percentage of the dark matter is made of primordial black holes, we could bring back some of the WIMPs that were ruled out or not?
Actually, it's quite the opposite. And this is some of the slides that I wanted to show you. I had to skip them, but let me show you this plot. Let me show you actually this one, and then I'll give you the technical details later on if you're interested. It is in principle possible to perform. So again, we said earlier that in principle, because of the no-hair theorem, if you see a black hole, it's just a black hole. You don't know what is its origin. But the fact is that, again, the formation scenarios for these objects, they leave an imprint on the mass function of these objects and on the environment. Now, there are observations that you can perform with interferometers, gravitational wave interferometers and other experiments that would tell you that what you're observing as a primordial black hole and not an astrophysical one. And one example, I can give you more, but one example, a simple example, is that if you observe the merger of subsolar black holes, if you see the gravitational waves coming from that system, then you know that it's not an astrophysical black hole, because we don't know any astrophysical channel to collapse stars with a mass of less than 1 solar mass. So if you make this type of observations, then you know that these objects are primordial, and you know that if you have primordial black holes, then there should be, because they cannot be all of the dark matter for the arguments that I just mentioned, then they would have dark matter around them, okay? And because of their formation scenario. And this cloud of dark matter actually would produce, if they were WIMPs, if it was made of WIMPs, it would produce an annihilation radiation which is so large that is essentially, ruled out by many, many orders of magnitude by current observations of gamma rays and things like that. So the line of the argument is the opposite. I mean, not only you cannot reconcile WIMPs, but if you observe even like one or a handful of these primordial black holes, you can probably rule out many more WIMP scenarios and beyond the standard model extensions.
I would say that it's a good time to stop. We have some refreshments in front, so let's thank our speaker again.
Thank you.